Take a moment and press your hand against the surface before you. A desk, a wall, a stone. It feels firm, dependable, solid. That solidity, that sense of permanence, is an illusion crafted by atoms, themselves fragile constructs of even smaller things. Look closer, beyond the electrons swirling in vast, empty orbits, and you find the nucleus, a dense cluster at the heart of every atom. And within that nucleus, beside the positively charged protons, lie the neutrons, silent, neutral, the invisible partners that make stability possible. But here is the paradox that should stop you cold. Remove a neutron from its atomic home, let it drift free, and it dies. In about 15 minutes, it decays into a proton, an electron, and a whisper of energy carried away by a neutrino. 15 minutes. That is the lifespan of the very particle that makes your body, your world, and your universe possible. How can something so unstable form the bedrock of reality? The question cuts deeper still. If the neutron, the so-called glue of matter, cannot endure on its own, is it real in the way we think of reality? Or is it something more elusive, a storm sustained by context, a shadow of forces rather than a thing unto itself? For centuries, humanity sought the indestructible, the indivisible, the eternal bricks of existence. The Greeks named them atomos, uncuttable. Centuries later, we thought we had found them in the atom itself. Then protons, neutrons, and electrons took the role of building blocks. But time and inquiry stripped away these illusions, revealing that the things we thought solid are instead unstable, contextual, contingent. The neutron is perhaps the most haunting of these revelations, a particle that gives stability to the universe, yet collapses when left alone. Imagine a universe without neutrons. Protons, repelling one another with relentless electric force, would refuse to bind together in any but the simplest atom, hydrogen. There would be no helium, no carbon, no oxygen, no heavy elements at all. No stars could burn, no planets could form, no life could ever emerge. The neutron, silent and uncharged, allows the universe to exist by holding protons apart while binding them together. Without it, reality would be a barren wasteland of lightest atoms, a cosmos without structure or complexity. And yet, this silent architect of existence is a ghost when taken out of its sanctuary. A free neutron crumbles back into other forms, its life measured in mere minutes. Our very survival depends on something that should not last, something that is not permanent, but precarious. This is the contradiction at the heart of reality. A neutron is both fragile and essential, fleeting and enduring, unstable and yet indispensable. It is the paradox of existence itself, crystallized in a particle. What then does it mean to call it real? Some scientists would answer with pragmatism. Neutrons are as real as anything else we can measure, track, or use. We detect their presence in reactors, harness them in medical imaging, watch their scattering reveal the hidden structures of matter. But beneath that pragmatic confidence lies unease, for the neutron's instability, its contradictions, hint at truths we have yet to grasp. There is a haunting beauty in this fragility. Consider, the neutron, born in the violent furnace of stars, is cast outward into the cosmos. It decays swiftly, but not instantly. Its 15-minute half-life is long enough for it to shape the chemistry of the universe, to play a role in cosmic evolution, to scatter and fuse and stabilize. It is as if the neutron exists in defiance of oblivion, a storm that must collapse, but not before it leaves its indelible mark. And when neutrons are crushed together in unimaginable numbers, as in the collapsed hearts of massive stars, they form neutron stars, cosmic objects of almost inconceivable density. A single teaspoon of neutron star matter weighs more than a mountain. Here, neutrons no longer decay, for gravity's grip and nuclear forces crush them into endurance. In the right context, the fragile ghost becomes the most enduring form of matter in the universe. Context is everything. So we begin with a question not just of science, but of philosophy. Is the neutron real, or is it a fleeting illusion, a temporary knot of forces that only persists in certain conditions? Is reality built of permanent bricks, or of storms given shape, lasting just long enough for the cosmos to unfold? The neutron forces us to confront what we mean by real. If reality must endure forever, then the neutron fails. If reality is what persists long enough to shape the world, then the neutron is more real than almost anything else. Without it, there would be no stars, no earth, no hand to press against the table and feel solidity.
And yet, we must face a darker possibility. The neutron's instability, its contradictions may be signs of something deeper. Anomalies pointing toward hidden physics, portals to unseen realms, forces we have yet to name. The neutron may be the key that cracks open not only the structure of matter, but the very fabric of reality itself.
So we begin with a hand on a table, with solidity that feels certain. We peel back the layers and find a storm of paradox, a particle that is both the glue of existence and the ghost of its own undoing. A particle that binds stars yet decays in silence. A particle that forces us to ask the most unsettling question of all. When even the neutron dissolves under scrutiny, what does it mean to be real? This is where our journey begins, at the fragile heart of matter, where stability itself unravels into mystery. And the further we go, the more we will find that the neutron is not just a particle, but a mirror, reflecting the precarious balance on which all reality rests. But if the neutron is this unstable, why has it not unraveled the universe itself? What hidden balances, what deeper laws hold the cosmos together in the face of such fragility? That is the mystery that awaits us.
The neutron is a paradox given form. It sits at the very heart of every atom heavier than hydrogen, yet it defies permanence. It is indispensable and yet unstable. A neutron locked inside a nucleus may endure for billions of years, longer than the lifetime of most stars, and yet a neutron set free from that sanctuary crumbles in just 15 minutes. What are we to make of such a contradiction?
Science thrives on paradoxes because they reveal the limits of our understanding. But this one cuts deeper, for it touches on the foundations of reality itself. If matter's stability rests upon something that is not itself stable, what does that say about the universe? Is reality built not upon unshakable foundations, but upon shifting sands that endure only because of balance and context? The theme of our story is born here. The neutron forces us to question the very idea of permanence. For centuries, humanity sought eternal, indivisible particles, atoms, protons, neutrons, electrons, things that could not be destroyed, the bricks of creation. The neutron was welcomed into this company as the invisible twin to the proton, balancing charges, providing mass. But then the revelation came. It decays. It is not eternal, it is not immutable, it is conditional. And in that condition lies the haunting truth. Stability is not about permanence, but about balance. Neutrons exist because the universe allows them to exist in certain contexts. Outside those contexts, they fail. Inside them, they thrive. Perhaps reality itself is like this, not built upon eternal stones, but upon relationships, contexts, conditions that hold for a time before dissolving. We see this paradox echoed throughout the cosmos. In stars, neutrons are created and destroyed in nuclear reactions, mediating the alchemy that forges heavier elements. Without neutrons, carbon and oxygen would never exist, and life as we know it could never arise. Yet the same neutron, when stripped from the nucleus, loses its grip and dissolves into other particles. It is both the architect of complexity and a fleeting ghost. This paradox extends to the human level. We crave permanence, solid ground beneath our feet, truths that do not shift, certainties that do not crumble. Yet the neutron whispers that even the most solid things are fragile storms. The desk beneath your hand, the rock in your palm, the mountain in the distance, all depend on neutrons that decay if they stand alone. Solidity itself is an illusion made possible by instability. Physicists frame this paradox in technical language. The neutron undergoes beta decay, transforming into a proton, an electron, and an antineutrino. But this language hides the deeper question. What does it mean that the universe is stitched together by things that cannot last? What does it mean that the essence of stability is impermanence? Consider this thought experiment. Imagine the universe without neutrons. Protons, all positively charged, would repel one another with ferocity. No stable nuclei heavier than hydrogen could form. No helium, no carbon, no oxygen, no iron. No stars to burn, no planets to form, no chemistry, no life. The cosmos would be reduced to a thin haze of hydrogen gas, a barren expanse of simplicity. Now imagine the opposite extreme, a universe where neutrons were too stable, never decaying. Neutrons would dominate over protons, and atoms as we know them could never form. Chemistry would collapse into monotony, stars might never ignite, life would again be impossible. Our existence depends on this precarious balance, a neutron that decays just quickly enough to avoid overwhelming the universe, yet slowly enough to allow complexity to arise. 15 minutes. That is the timescale upon which existence hangs. A single particle's half-life has shaped the destiny of galaxies. This is the paradox of the neutron, fragile yet foundational, unstable yet indispensable.
And it raises a larger question, one that reaches beyond physics into philosophy. What does it mean to be real? Must reality be eternal to deserve the name? Or is reality defined by persistence, by influence, by endurance across the scales that matter?
By one definition, the neutron fails. It is not permanent, it is not eternal. By another, it succeeds triumphantly. It has shaped stars, worlds, and life. It has endured long enough to matter, and in doing so, it has given rise to everything. This is the theme that will guide us through the rest of the journey. Reality is not permanence, but process. Not immutability, but persistence. The neutron is not real in the way a stone is real. It is real in the way a flame is real, a balance sustained, an event enduring in time, fragile yet profound. As we move deeper into the story, we will see how this paradox unfolds across scales. We will explore how neutrons stabilize nuclei, how they create stars, how they collapse into neutron stars of unimaginable density. We will confront the mysteries of neutron decay, the anomalies that hint at new physics, the possibility that neutrons might be doors into hidden realms. Each step will return us to this theme. Reality is balance, not bedrock. But for now, we sit with the paradox. The hand on the table feels solid. The table feels permanent. Yet all of it rests on neutrons, particles that should not endure. Our sense of permanence is sustained by things that are themselves impermanent. That is the neutron's riddle, and it is also our own. For if neutrons are fragile storms, then so too are we. Our lives, our civilizations, our very species, temporary patterns sustained by balance, destined to decay, yet enduring long enough to matter. In the neutron we see not only the structure of the universe, but also the mirror of our own existence. So we ask the question that will haunt every step of this journey: are neutrons even real, or are they illusions of context, ghosts of balance, storms that we mistake for stones? The paradox will not let us go. And in chasing its resolution, we may uncover not only the nature of neutrons, but the nature of reality itself. But if the neutron is a storm, how did we discover it? How did humanity first glimpse this ghost particle that hides at the heart of atoms? That is where the next part of our journey takes us. Every revolution in science begins with a mystery, a gap between what we expect and what we observe. For centuries, the atom was thought to be indivisible, the uncuttable bedrock of existence. But by the early 20th century, that vision had already begun to unravel. Electrons had been discovered, carrying negative charge. Protons had been identified, carrying positive charge. And yet, something was missing. The numbers didn't add up. When scientists measured the mass of atoms, they found a puzzle. Helium, for example, with its 2 protons and 2 electrons, weighed more than the combined mass of those particles should allow. The discrepancy grew with heavier elements. There was extra weight hidden in the nucleus, a kind of phantom mass that could not be explained. Something invisible lurked there, balancing charge and adding heft. By the 1920s, speculation ran wild. Some imagined that electrons might somehow be trapped inside the nucleus alongside protons, forming a dense mixture that gave atoms their mass. Others proposed entirely new particles. But none of these ideas fit the evidence. The nucleus remained a black box, stubbornly defying explanation. It was in 1932 that the mystery was finally cracked open by James Chadwick, working in Cambridge at the Cavendish Laboratory. The path to discovery began with curious experiments in which beryllium was bombarded with alpha particles, helium nuclei ejected at high speed from radioactive decay. When the alpha particles struck the beryllium, they seemed to knock something loose, a new kind of radiation that passed through matter with uncanny ease. At first, many believed this radiation was gamma rays, high-energy photons. But gamma rays could not explain the strange effects that followed. When this radiation struck paraffin wax, it ejected protons with remarkable force, as if something with mass was colliding with them directly. Light could not do that. Chadwick reasoned that the mysterious radiation was not light but a new kind of particle, massive like the proton, but carrying no charge. A neutral particle hidden in the heart of the nucleus. The neutron had been glimpsed. The announcement was electrifying. In a single stroke, the nuclear puzzle was solved. The missing mass was accounted for. The mystery of how protons clustered together in nuclei, despite their mutual repulsion, was clarified. Neutrons, uncharged and heavy, could act as buffers, holding the nucleus together without adding further electric repulsion. Yet the neutron was more than just an accounting trick. It was a revelation. Until that moment, matter had been imagined as charge balancing charge, protons and electrons, positive and negative. The neutron broke that symmetry. It was invisible to the eye and undetectable by charge, but its presence shaped everything. It was the ghost in the atom, unseen yet indispensable. And with its discovery came a cascade of consequences. Neutrons, because they carried no charge, could slip easily into nuclei, making them perfect probes for nuclear reactions. Within years, scientists realized that neutron bombardment could split atoms apart, nuclear fission, releasing energies that dwarfed anything previously imagined. The chain of events that began with Chadwick's discovery would culminate in both the darkest weapon humanity had ever known and the most potent source of energy we had ever harnessed. But in 1932, before those consequences unfolded, there was only awe. A hidden particle had been revealed, one that explained the very stability of matter. The world was not built solely from positive and negative charges. It was built also from silence, from neutrality, from something that did not announce itself with force but quietly bound the universe together. And yet, even here, paradox lurked. For the neutron's neutrality, its invisibility, made it strangely ghostly. It was easy to overlook, easy to dismiss. Unlike the electron, it carried no charge to betray its presence. Unlike the proton, it carried no obvious stability. Its discovery required not just keen observation, but a leap of imagination, a willingness to believe in something that could not be seen directly. The neutron, then, was born into paradox, essential yet invisible, solid yet unstable, real yet elusive. And perhaps that is why its discovery resonates so deeply. It embodies the theme that will carry us through this journey, that reality is not found in permanence or in obviousness, but in the fragile, the hidden, the ghostly forces that sustain existence. From the very moment of its revelation, the neutron changed the story of the atom. No longer was matter a simple balance of positive and negative. Now, at the heart of every nucleus, there was neutrality. And neutrality, it turned out, was the true foundation of complexity. But even in those first days, questions lingered. How long could a neutron last outside the nucleus? Was it truly stable, or was it hiding fragility beneath its silence? Within a few years, experiments revealed the shocking answer. A free neutron is doomed. Left alone, it decays into a proton, an electron, and a neutrino, its lifetime measured not in cosmic spans, but in mere minutes. The discovery that began with hidden mass thus ended with a haunting contradiction. The particle that explained the stability of matter was itself unstable. The universe was built upon a ghost. It is here that our theme crystallizes. Neutrons are real. We can measure them, manipulate them, build reactors and detectors from them. And yet, they are not real in the way we expect. They are not permanent. They do not endure forever. Their reality is contextual, conditional, contingent. Inside nuclei, they live for eons. Outside, they crumble swiftly.
This paradox would ripple outward, shaping not just nuclear physics but cosmology, philosophy, even our conception of reality itself. For if the neutron is unstable, what else in the universe rests on fragile balance rather than immutable foundation? The story of the neutron's birth is thus not just a tale of scientific discovery, but the opening of a door into existential wonder. It is a reminder that the deepest truths often hide in silence, that the things we take for granted, the solidity of the world, the permanence of matter, are fragile illusions. Beneath them lies neutrality, fragility, paradox.
James Chadwick's discovery in 1932 earned him the Nobel Prize, but its true legacy was something greater. It forced humanity to see that reality is not simple, not permanent, not obvious. It is subtle, fragile, elusive. It is a storm of contradictions balanced just long enough to give rise to stars, planets, life. The neutron was born into paradox, and with it, our understanding of reality itself was reborn. But as with every revelation, the birth of the neutron raised new questions. If it is neutral, what holds it together? If it is unstable, what sustains it within the atom? And if it can decay, what does that mean for the fate of the universe itself? That is where the next step of our journey takes us. The story of the neutron pivots quickly from revelation to paradox. When James Chadwick unveiled it in 1932, it seemed at first to be the missing puzzle piece, the long-sought solution to the mysteries of atomic mass and nuclear stability. Here, at last, was the invisible partner of the proton, a silent stabilizer that allowed nuclei to exist. But the triumph of discovery soon gave way to a deeper, more unsettling realization. The neutron is not truly stable. Outside of a nucleus, it falls apart. In the laboratory, free neutrons can be captured, slowed, and measured, and each time the same haunting result emerges. After about 15 minutes, half of them are gone. They disintegrate into a proton, an electron, and a neutrino, their mass and energy redistributed into new forms. In the language of physics, they undergo beta decay. In the language of philosophy, they dissolve, unable to exist on their own. The paradox is stark. The neutron is the glue of matter, the very particle that allows protons to gather together without tearing themselves apart. Without neutrons, nuclei heavier than hydrogen could never exist, and yet the neutron itself is fragile, unable to endure isolation. It survives only when sheltered by protons, only when bound into the complex structure of the nucleus. Alone, it dies. This contradiction unsettles our most basic intuitions about reality. We imagine foundations as stable, enduring, unshakable. Yet here we find that the very foundation of matter is contingent, contextual, dependent. The neutron is real, but not in the sense of permanence. It is real in the sense of balance, of conditional endurance. Why should this be so? At the level of quarks, the neutron is composed of two down quarks and one up quark, bound by the strong nuclear force. The proton, by contrast, is two up quarks and one down. The difference seems trivial, a simple rearrangement of the same building blocks. Yet that small difference determines everything. Protons are stable, neutrons are not. The up quark is ever so slightly lighter than the down quark, and that mass difference tips the scales. It is enough to render the proton effectively eternal and the neutron fragile. This minute asymmetry echoes outward across the cosmos. It is the reason our universe is built the way it is. If the masses of quarks had been shifted by the smallest fraction, if the balance had tipped another way, protons might not be stable at all. Neutrons might have reigned, or neither particle might have endured long enough to build nuclei. The delicate balance between quarks defines the very possibility of atoms, stars, and life. And so we face the paradox in full. The neutron is both indispensable and unstable, both the glue of existence and the ghost of its own undoing. This paradox grows sharper when we examine how neutrons behave in different contexts. Inside stable nuclei, they can endure for billions of years, outlasting stars. Within the dense crush of a neutron star, they can persist indefinitely, locked in place by gravity's overwhelming grip. But remove them from these contexts, and they wither quickly. The neutron, then, is not real in isolation. Its reality is relational, conditional, emergent. Here we glimpse a deeper truth, one that resonates beyond physics. Reality itself may be like this, not built from eternal bricks, but from balances, processes, conditions. What we call real is what endures long enough, what persists in context, what sustains patterns across time. The neutron forces us to abandon the illusion of permanence and embrace the fragility at the heart of existence. Consider the irony. When we press our hand to the table, when we lean against a wall, when we marvel at the stability of stone or steel, all of it rests on neutrons that, in isolation, would crumble in minutes. Solidity is an illusion sustained by fragile storms, endurance purchased not by permanence but by balance. The neutron paradox has also driven some of the deepest experiments in modern physics. Scientists measure its lifetime with exquisite care, counting how quickly free neutrons decay in beam experiments or in bottle traps. Intriguingly, these methods yield slightly different results, a discrepancy that has haunted physics for decades. Is it simply experimental error, or is the neutron pointing us toward hidden physics, toward particles or forces that lie beyond the standard model? This is why the neutron is more than just a nuclear building block. It is a doorway. In its fragility and its contradictions, it hints at truths we have not yet grasped. Some physicists speculate that neutrons might occasionally decay into dark matter particles, slipping into a hidden sector of the universe. If that is true, then the neutron is not only fragile, but also a messenger, pointing us toward the unseen. Yet even if no such hidden decay is found, the paradox remains. The neutron is a particle that cannot stand alone, yet it sustains the universe. Its reality is not in its permanence, but in its persistence. It exists because it endures just long enough in the right contexts to matter. Philosophically, this challenges our deepest assumptions. For centuries, we sought eternal atoms, immutable essences. The neutron reveals that reality is not about essence at all. It is about process. To exist is to endure for a time, to sustain balance against dissolution. The neutron is real, not because it is unchanging, but because it persists long enough to hold the universe together. This reframes our own existence. We too are fragile storms, held together by balances, destined to decay. We endure not forever, but long enough to matter. In the neutron's paradox, we see a mirror of ourselves. And so, the question lingers, are neutrons even real? If reality is permanence, then no. If reality is persistence, then yes. They are as real as the stars they build, as real as the bodies they sustain, as real as the universe they hold. Their fragility does not diminish their reality, it defines it. The paradox of the neutron is not a flaw to be explained away, but a truth to be embraced. Reality is not bedrock, it is balance, not permanence but process, not stones but storms. And yet, the paradox opens onto a new mystery. For if neutrons are so fragile in isolation, what allows them to endure so long inside nuclei? What hidden balances make them stable in stars, in matter, in us? That is where the next stage of our journey leads, into the atomic nucleus itself, where neutrons do their most essential work, holding the world together. At the heart of every atom lies a paradox of forces. Protons, each carrying a positive electric charge, should repel one another with fierce intensity. Like charges do not attract. In fact, if you place two protons close together, the Coulomb force between them is immense, orders of magnitude stronger than the pull of gravity that binds planets and stars. By every instinct, a nucleus should fly apart, its pieces scattering into the void. And yet, it holds. The world endures. The question is why? The answer, silent and often overlooked, is the neutron.
Neutrons carry no charge. They neither repel nor attract electrically. To the force of electromagnetism, they are ghosts. But they are not irrelevant. Quite the opposite. They are the unsung architects of stability, the invisible scaffolding that holds the nucleus together. Without them, the forces of repulsion would tear every atom heavier than hydrogen apart.
The glue is the strong nuclear force, the most powerful of nature's four fundamental forces, binding quarks together into protons and neutrons, and binding those nucleons together into nuclei. Unlike the electromagnetic force, which grows weaker as charges separate, the strong force saturates. It acts only at short ranges, distances comparable to the size of a nucleon itself, but within that range, it is overwhelming. Neutrons make this binding possible by changing the balance. When a neutron sits between protons, it contributes mass and participates in the strong nuclear force without adding electric repulsion. It is the quiet mediator, the peacekeeper in a war of charges. Protons alone would never tolerate each other's company. Neutrons enable the truce that makes atoms possible. This explains why hydrogen, with its single proton and no neutrons, is the simplest and most abundant element. It exists because a lone proton does not need neutrons to stabilize it. But the moment you try to build something heavier, helium, carbon, oxygen, neutrons become essential. They are the dark matter of the nucleus, invisible, yet decisive. Their silent presence permits diversity. Consider carbon, the backbone of life. Its nucleus contains 6 protons. Without neutrons, those 6 positive charges would explode apart. But with 6 neutrons woven among them, the nucleus stabilizes. The balance holds. Life as we know it depends on this subtle arithmetic. Neutrons tempering protons, neutrality stabilizing charge. Even more striking is iron, the element forged in the hearts of massive stars and strewn across the cosmos in supernova explosions. Its nucleus contains 26 protons. Without neutrons, it would disintegrate instantly, but with 30 neutrons balancing the forces, it endures as one of the most stable nuclei in the universe. It is no coincidence that iron sits at the pinnacle of nuclear stability, the element around which stellar alchemy pivots. The quiet work of neutrons sustains it. This balance reveals a deeper truth. The universe itself is a negotiation, not a monolith. Reality is not the triumph of permanence, but the victory of balance over chaos. Neutrons are the embodiment of that truth. They do not announce themselves with electric charge. They do not endure forever in isolation. But within the right context, they allow the impossible. Protons, side by side, stability where none should exist. The power of the neutron's role becomes clearer when we explore isotopes. An isotope is simply an element with the same number of protons, but different numbers of neutrons. Hydrogen has 3 isotopes: protium with no neutrons, deuterium with 1 and tritium with 2. All share the same chemical identity, 1 proton, 1 electron, but their stability depends on neutrons. Protium is stable, deuterium is stable, but tritium is unstable, decaying with a half-life of just over 12 years. Here, neutrons do more than stabilize. They define the boundaries of existence. Too few, and the nucleus cannot hold. Too many, and the balance collapses. The periodic table itself is thus a delicate map of neutron balance. For each proton count, only certain neutron numbers produce stable nuclei. Venture too far from those ratios, and the nucleus decays, emitting particles, transforming into other elements. The chart of Nuclides is a landscape sculpted by neutrons, a terrain where stability is a narrow path and instability yawns on either side. This raises a haunting realization. The world we inhabit, the elements we rely on, the chemistry of life itself, are possible only because neutrons exist in just the right proportions. If the neutron's properties were even slightly different, if its mass or decay rate shifted by the smallest fraction, the entire map of stable nuclei would change. Stars might never forge carbon or oxygen. Life might never arise. The neutron is not merely a passive participant in the nucleus. It is the gatekeeper of possibility. And yet, its role is not simple. Neutrons stabilize, but they also introduce fragility. Too many neutrons can make a nucleus unstable, prone to radioactive decay. This is why heavy elements like uranium are unstable. Their large neutron excess pushes them beyond balance, forcing them to shed mass and energy in search of stability. The neutron, paradoxically, both holds the nucleus together and defines the limits of how much can be held. It is both glue and executioner. The paradox of the neutron deepens further when we look to the stars. In the violent cores of massive stars, protons fuse into helium, releasing energy. But as fusion climbs the periodic table, neutrons become ever more essential. Without them, the chain of nuclear reactions would stall, and the star's life would end prematurely. Instead, neutrons allow the furnace to build heavier elements, culminating in iron. When the star dies in supernova, those elements scatter across the cosmos, seeding planets and life. The neutron, silent in the nucleus, thus shapes the history of galaxies. The same holds in neutron capture processes, the slow and rapid pathways that build elements heavier than iron. Gold, platinum, uranium, all owe their existence to neutrons captured in the chaos of stellar explosions. Neutrons are the chisels of cosmic alchemy, carving the universe's richness from hydrogen's simplicity. The paradox remains. The neutron is fragile, unstable outside the nucleus. Yet inside, it is indispensable, the architect of stability, the sculptor of diversity. It is the quiet partner in every atom, the uncelebrated force without which the universe would collapse into barren hydrogen. So we must return to the question, are neutrons even real? They cannot endure alone. Their existence is defined by context. But perhaps this is the very essence of reality, not permanence, but relationship. The neutron is real because it allows reality to exist, even if it cannot survive in solitude. And still, the mystery deepens. For if neutrons are so essential to the nucleus, what happens when they escape its grip? What hidden truths emerge when they are free, decaying, fragile? The next stage of our journey leads us from the nucleus into the wider universe of the neutron's strange behaviors, scattering experiments, neutron stars, and the anomalies that hint at new physics beyond the known. The neutron is glue, but glue too has its limits. What happens when the bonds fail? Beneath the veil of ordinary matter lies a battlefield of unimaginable forces, a place where the familiar rules of chemistry, stability, and life itself teeter on a razor's edge. To cross the threshold into the heart of the atom is to step into a domain of tension so profound that, without its delicate balancing act, the universe would unravel into chaos. Here, neutrons emerge not as silent spectators, but as guardians.
the shadowy arbiters of existence, holding the fury of the protons at bay.
Imagine, for a moment, the nucleus stripped of its neutrons. What remains is a prison of protons alone, each bearing the same electric charge, each repelling the other with a force as relentless as gravity is patient. If left unchecked, this repulsion would be catastrophic. The nucleus would fly apart in an instant, an explosion of like charges shattering the possibility of structure. Atoms would never form, stars could never ignite, planets could never coalesce. Chemistry itself, that exquisite dance of electrons and bonds, would never have been born. It is the neutron, paradoxically neutral, that steps into this fray and restores order from impending collapse. The neutron's gift is separation. By slipping between protons like a silent mediator, neutrons dilute the Coulomb repulsion that would otherwise tear the nucleus apart. They do not carry a charge, yet they exert their presence through the strong nuclear force, that most enigmatic of nature's bonds, binding protons and neutrons alike in a grip so fierce it defies the screaming protest of electromagnetism. The result is stability, a fragile stability to be sure, but one sufficient to allow the edifice of matter to rise. Consider the lightest nuclei, hydrogen and helium. Ordinary hydrogen with its lone proton needs no neutron to survive. Its singular charge holds together as a solitary point. But add one more proton and catastrophe looms. Helium with two protons would be impossible, its mutual repulsion intolerable. Yet insert two neutrons and suddenly harmony is restored. The neutrons interlace the protons in a compact knot, their strong nuclear bonds overpowering the Coulomb force. In this simple act, the architecture of matter expands, and the elemental foundation of stars is secured. This principle echoes upward through the periodic table. Carbon, oxygen, iron, each requires a balance of protons and neutrons, a dance between charge and neutrality, between repulsion and cohesion. Too few neutrons, and the nucleus becomes unstable, fissile, prone to decay. Too many neutrons, and the balance tips again, creating isotopes that drift into instability. There is no permanent equilibrium, only a narrow window where neutrons and protons coexist long enough to support the miracle of structure. Beyond that threshold, matter unravels into radiation, fragments, and energy. To cross this threshold is to recognize the neutron's role not merely as a stabilizer, but as the arbiter of possibility. The neutron is not a passive filler of space. It is the hinge upon which existence swings. It creates the possibility of complex atoms, which in turn form molecules, which in turn weave into the fabric of biology, geology, and consciousness. Strip the neutron away, and what remains is a universe reduced to a barren haze of hydrogen. No stars beyond the faintest, no heavy elements, no planets, no life. The neutron is the silent engineer of complexity itself, yet this stability comes at a price. For the neutron, though essential within the nucleus, is treacherous when left alone. Isolated, it is unstable, disintegrating within minutes into a proton, an electron, and a ghostly anti-neutrino. This duality, stability in the collective, decay in isolation, renders the neutron a paradox. It is indispensable within the atomic fortress, yet transient and doomed when exiled. It exists only to serve its role as mediator, its life tied inextricably to its companions. The neutron is not a particle of independence, but of relationship defined by its place within the whole. The nucleus, then, becomes a battlefield of balance, the strong nuclear force binding protons and neutrons together, the Coulomb repulsion pushing protons apart, and the delicate arithmetic of neutron numbers determining whether stability or decay will prevail. Every element, every isotope, every fragment of matter reflects this balance, as if the universe itself were continually negotiating the terms of its own endurance. To exist is to balance on the knife's edge of these forces, and the neutron is the blade's hidden spine. It is no coincidence, then, that the processes that forge the universe are deeply tied to neutrons. In the heart of stars, Neutrons emerge in fusion reactions, shaping the abundance of elements. In the throes of a supernova, torrents of neutrons flood into collapsing matter, creating the heavy elements that seed planets and life. In neutron stars, the cosmic tombs of massive suns, neutrons themselves form vast oceans of degenerate matter, locked in a pressure so fierce that even atoms are annihilated, leaving only a neutron sea. From the smallest nuclei to the grandest stellar remnants, neutrons define the arc of cosmic evolution. And yet questions linger in the shadows. Why are neutrons unstable in isolation, but stable within the nucleus? Why does the strong nuclear force bind as it does, overpowering Coulomb repulsion at short distances yet faltering at larger scales? What dictates the neutron-to-proton ratios that carve the line between stability and decay? These are not mere technical curiosities, but existential riddles. They hint at mysteries buried deeper in the fabric of reality, as if the neutron itself were a messenger from realms beyond our comprehension, whispering of laws not yet uncovered.
Without neutrons, the universe would collapse into simplicity, stripped of diversity and wonder. With neutrons, the cosmos unfolds into stars, planets, chemistry, and life. But their very necessity raises a haunting question. Are neutrons truly fundamental, or are they themselves the product of a deeper architecture, a scaffolding of quarks and gluons woven into forms we barely understand? To peer into the nucleus is to glimpse not resolution, but another door opening into a corridor of enigmas.
In this crossing of the threshold, we find ourselves staring into the nucleus not as a static fortress, but as a battlefield of forces, where neutrons hold the line against collapse, enabling the possibility of matter and meaning. And yet, as with all thresholds, crossing it leads only deeper into mystery. If neutrons are the guardians of existence, then what, we must ask, guards the guardians?
Stability has always been the dream of civilizations. Empires rise with the promise of order and crumble under the weight of their own excess, just as individuals seek balance between the forces pulling them in every direction. This same tension underlies the very structure of the universe, hidden not in politics or philosophy, but in the nucleus of the atom. And there, neutrons stand as the silent analog to our human story, the invisible mediators who, by existing in the shadows, hold the chaos at bay.
Imagine Rome at its height, a sprawling empire stretched between the Mediterranean and beyond. Its cohesion depended not just on legions or laws, but on the fragile balance between cultures, religions, and ambitions. Remove one element, allow one force to dominate unchecked, and the system teetered toward collapse. The neutron plays this same role within the nucleus. It does not proclaim its presence, it does not carry a charge, but without it, the republic of protons explodes into ruin. Civilization and nucleus alike survive only through the hidden architecture of balance. This parallel is more than metaphor. Human beings, like protons, are restless, charged with desire and ambition. Left alone, they repel each other, pushing society into conflict. What we call stability, in families, nations, or individuals, requires something quieter, less obvious, a force without agenda. In the political world, it might be trust, compromise, or a shared belief. In the atomic world, it is the neutron. Both are uncelebrated yet essential. Both are mediators of impossible tensions. To ignore them is to risk collapse. But there is another layer to this analogy, one that cuts deeper into the human soul. Just as neutrons decay when isolated, so too does the human being falter in solitude. Strip a neutron from its nuclear home, and within minutes it fractures into other particles. Strip a human from the network of community, love, and responsibility, and the result is dissolution. Stability is not a property of the individual, but of the collective. It is in the weave of relationships, whether human or nuclear, that persistence is found. This truth has haunted civilizations. The Mayans, the Greeks, the empires of China, Each built great systems that balanced competing forces, only to watch them fail when that balance was broken. The neutron's lesson is that endurance is never permanent. It must be maintained, rebalanced, continually negotiated. The moment one assumes stability to be a natural right, it begins to unravel. In this sense, the neutron is not simply a particle but a parable. And yet, as with human societies, there is fragility in the numbers. Too many neutrons and the nucleus becomes unstable. Civilizations too heavy with bureaucracy, tradition, or hidden power implode from within. Too few, and they collapse under the violence of unchecked charge. There is no perfect equilibrium, only a shifting range within which survival is possible. Isotopes wobble on either side of stability, just as societies wobble between freedom and order, chaos and rigidity. The neutron, like history, whispers that balance is always temporary. Even at the personal level, the analogy holds. Each of us is a nucleus of forces, desire and duty, fear and hope, passion and restraint. Without something to mediate, to hold these contradictions together, the self disintegrates. The neutron, invisible yet indispensable, is mirrored in the unseen habits, beliefs, or relationships that hold a life intact. Perhaps it is love. Perhaps it is faith. Perhaps it is simply the willingness to endure. But like the neutron, it is never celebrated until it is gone, and collapse rushes in. This story of hidden balance extends beyond philosophy into the very fabric of human endeavor. Consider the Gothic cathedrals of medieval Europe, vast stone structures that should by all accounts have toppled under their own weight. They stand because of counterforces, arches and buttresses, hidden structures distributing stress. The neutron is the buttress of matter, the unseen support that allows the cathedral of the universe to rise. Remove it, and the spire collapses, as surely as a society collapses when its invisible supports fail. Yet there is also a darker reflection. Neutrons, for all their stabilizing power, also carry the seed of destruction. Too many neutrons can render a nucleus unstable, causing radioactive decay. So too with civilizations, the very tools that stabilize can, in excess, become corrosive. Tradition calcifies into tyranny. Unity dissolves into conformity. Balance requires not just supports, but limits, not just neutrons, but the right proportion of them. The neutron teaches us that excess and deficiency alike lead to collapse, and so the human quest for balance mirrors the cosmic one. It is not permanence we inherit, but the responsibility of maintaining equilibrium. The neutron's silence is deceptive. It embodies a lesson that resonates across every scale of existence. Balance is never obvious, never loud. It hides in the spaces between, in the neutral ground where opposites meet and tension is absorbed. Without it, nothing endures. With it, galaxies, civilizations and lives may flourish, but only for a time. As we look inward, from the sweep of empires to the beating of a single heart, the neutron's role becomes something more than physics. It becomes a metaphor for survival, for the precarious act of holding together the unstable contradictions of existence. The neutron is not simply real in the laboratory, it is real in the narrative of humanity itself. To cross into this understanding is to glimpse that the quest for balance is not merely cultural or personal, it is woven into the very architecture of matter. And here lies the unsettling question: if neutrons are the mediators of existence, what mediates us? Who or what plays the neutron's role in the cosmos of human history, absorbing our tensions, preventing collapse? Is it faith, reason, or is it something still hidden, something unrecognized but indispensable? The neutron suggests that the answer may not be a force of grandeur, but a silent presence in the shadows, holding chaos apart so that order might endure, at least for now. They are born in fire. In the cataclysm of a supernova, in the silent crucible of stellar fusion, neutrons emerge in staggering numbers, filling the cosmos with their enigmatic presence.
Unlike protons, which proudly bear their positive charge, neutrons glide silently, unnoticed, neutral, and yet this very neutrality gives them power. The power to slip between worlds, to probe hidden structures, to transform matter itself. Their story is stranger than fiction, and their lives span the smallest laboratories to the densest stars. In the hands of scientists, neutrons become cosmic tools. Because they carry no electric charge, they can penetrate deep into matter without being deflected by the electric forces that scatter protons or electrons. Imagine an army of messengers slipping past defenses, revealing secrets hidden in the depths of steel, water, or even the fragile tissue of living things. This is the principle of neutron scattering, a method that allows us to see not with light, but with silence. Neutrons, released in beams from reactors or particle accelerators, pass through materials and emerge with patterns that reveal atomic structures. With them, we map the architecture of crystals, the motion of proteins, even the dance of magnetic fields. They are ghostly scouts, slipping between atoms, reporting back not in words but in patterns of probability. And then, at the farthest edge of astrophysics, neutrons take on a grander role. In the heart of collapsing stars, where gravity crushes matter with unspeakable force, protons and electrons fuse into neutrons. The result is one of the strangest objects in the universe, the neutron star. A single teaspoon of its matter weighs billions of tons, yet it spins with ferocious speed, emitting beams of radiation that sweep across the cosmos like lighthouses in the dark. These stars are laboratories of extremes, where neutrons are packed so tightly that the very laws of physics buckle. Do they form exotic superfluids? Do they create new states of matter? We do not know. But neutron stars remind us that the neutron is not a minor particle in the background. It is a builder of worlds and a harbinger of mysteries still unsolved. Closer to home, neutrons reveal another uncanny power: imaging. Unlike X-rays, which can damage tissue or bounce off dense materials, neutrons slip through many heavy elements with ease, while being strongly absorbed by light ones like hydrogen. This inversion of perception allows scientists to see water coursing through engines, fuel cells breathing in real time, or even the delicate moisture inside ancient relics without breaking them. Neutron imaging opens windows where light cannot go, offering us a glimpse into hidden flows and unseen processes. The neutral messenger becomes a lantern in the dark. But neutrons are not only observers, they are also actors in transformation. Nuclear reactors depend on their ability to strike atoms and split them apart. A single neutron colliding with uranium can unleash a storm of energy and more neutrons in turn, a chain reaction that powers cities or, in darker chapters of history, levels them. In this duality, we glimpse the neutron's paradox: stabilizer in one realm, destroyer in another. It is the quiet one, the neutral one, that tips the balance between creation and annihilation. Even in the laboratory, their strangeness continues to confound. Scientists trap ultra-cold neutrons, moving slower than a human walk, to measure their properties with exquisite precision. Do they wobble in ways we did not predict? Do they betray hidden symmetries or cracks in the standard model? Each experiment seems to whisper of possibilities, of forces unseen, as if the neutron is hinting that its story is not yet fully told. And so, the neutron lives a double life, ghostly and solid, stabilizer and destroyer, key to both the smallest measurements and the grandest cosmic events. It reveals, transforms, and sustains, all while remaining invisible, neutral, unnamed in the story of chemistry that glorifies electrons and protons. Yet, without neutrons, the stars themselves would have ended differently. Our bodies would never have formed, and the universe would lack its strange, hidden scaffolding. This is the life of the neutron, a life lived in silence, but one that echoes across galaxies. It is not a particle confined to a definition in a textbook. It is a character in the cosmic drama, moving unseen through the story of existence.
And just as with the human soul, its strangeness is inseparable from its meaning. But strangeness invites questions. Why do neutrons decay when isolated, but persist for billions of years inside nuclei? Why do they seem to slip into roles no one else can fill, from cosmic scaffold to destructive agent? Their neutrality is a mask, and beneath it lies a riddle. The next step is to ask, has our triumph in explaining neutrons been too neat, too assured? Or is there something hidden in their very silence that unsettles the foundations of physics? For a moment, it seemed the story was complete. The standard model of particle physics stood triumphant, its neat diagrams and equations capturing the known particles and forces with breathtaking precision. In its halls, the neutron found a comfortable home, 3 quarks bound together by gluons, a down-down-up triplet woven into a neutral knot of matter. The model told us how neutrons were born, how they lived, and even how they died. For decades, the narrative held, and the triumph felt secure. It was a story of elegance, of mathematics made flesh. Quantum chromodynamics, the theory of quarks and gluons, explained why neutrons did not unravel under the strain of their internal chaos. Experiments matched predictions with uncanny precision, from the way neutrons scatter off targets to the magnetic moment that hints at their inner structure. Here, at last, was the false victory, the illusion that the mystery had been tamed. Physicists proclaimed it. The neutron was solved. A composite particle, stable inside nuclei, unstable outside. A mean lifetime of about 15 minutes before it decays into a proton, an electron, and a ghostly antineutrino. What more was there to know? For a time, the neutron became a background actor in the theater of physics, a solved puzzle, a matter-of-fact building block in textbooks and lecture halls. The spotlight shifted elsewhere, to the Higgs boson, to dark matter, to cosmology's haunting riddles. The neutron, it seemed, had surrendered its secrets. But certainty is a fragile thing. For behind the neat numbers and tidy explanations lurked tiny discrepancies, so small they could almost be ignored. Almost. The first cracks appeared in the measurements of the neutron's lifetime. If theory was settled, then observation should converge to a single value, but it did not. Physicists devised 2 methods to catch the fleeting moment of a neutron's decay. One was the bottle method, in which ultra-cold neutrons are trapped in magnetic or material bottles and simply counted until they disappear. The other was the beam method, in which a stream of neutrons is observed, and the decay products, protons and electrons, are tallied. Both methods were ingenious. Both were designed to give us the same answer. And yet, they did not. The bottle method gave a lifetime of around 879 seconds, the beam method about 888 seconds, a gap of roughly 9 seconds. Trivial, you might think. But in the high temples of physics, where measurements are precise to a part in 10 million, such a gap is a thunderclap. The triumph now looked less like victory and more like a mask. Could the neutron's death hold secrets unimagined? Could it be slipping into dimensions unseen, decaying into particles beyond the standard model's grasp? What if the missing neutrons in the bottle were not decaying into protons at all, but into something else, something invisible? It was in this dissonance that the false victory revealed itself. The very particle once thought solved began to hint at new frontiers. Cosmologists noticed something uncanny. The measured neutron lifetime affects predictions for the early universe. The precise abundance of hydrogen and helium forged in the Big Bang depends on this number. Shift it slightly, and the cosmic story bends. Could the discrepancy between bottle and beam be whispering of physics hidden in the first minutes of existence? The standard model, once triumphant, now seemed too clean, too complete. Its walls, thought unshakable, trembled under the weight of anomaly. The neutron, the silent stabilizer of atoms, refused to stay silent. And so the midpoint arrives, the illusion of certainty, the false closure. The neutron is explained, yes, but explained too well in a way that cannot survive contact with reality. The triumph is hollow, the puzzle unsolved, the victory premature. The question lingers like a shadow. What does the neutron decay into when no one is watching? A proton, an electron, and a neutrino, or something else entirely? A dark sibling of matter, a portal to forces unnamed. We are left with an uneasy thought. Perhaps the Standard Model's perfection is itself a clue, the too neat bow on a gift hiding something far stranger beneath. And if the neutron, the very glue of matter, is not as we think, then what of the universe that depends upon it? The cracks widen slowly, like hairline fractures spreading through a sheet of glass. At first you might ignore them, dismiss them as imperfections, but then the lines grow longer, branching outward until the integrity of the whole pane trembles. So it is with neutrons. Once thought stable in their narrative role, they now splinter under scrutiny, their story no longer seamless but fractured with contradiction. The discrepancy in neutron lifetimes, 9 seconds of uncertainty between the bottle and beam methods, did not fade away with more measurements. Instead, it deepened. Laboratories across the world repeated the experiments, refining their techniques, eliminating sources of error, improving their statistics. But the gap remained. Each new dataset did not close the wound but widened it, a silent accusation against our understanding. The bottle method, elegant in its simplicity, traps ultra-cold neutrons and waits. One by one they vanish, either by decay or by escape. The survivors are counted, their decline a measure of life's brevity. Yet bottle experiments consistently give shorter lifetimes, about 879 seconds. Meanwhile, the beam method relies not on waiting but on watching. A stream of neutrons passes through detectors, and the protons born from decay are tallied. These counts imply a longer life, nearly 888 seconds. The difference may seem minor, but it is not. It suggests that something unseen is happening, something unaccounted for. In the world of physics, every second is a chasm, and 9 seconds, stubborn and unexplained, became a battlefield. Here, the bad guys enter, not villains of flesh and blood, but anomalies, doubts and questions that multiply like shadows. Is it possible that neutrons decay into channels unknown, slipping into states beyond our detector's reach? Some physicists whisper of dark matter, the invisible substance that outweighs all the visible stars and galaxies in the universe. What if neutrons occasionally decay into dark particles escaping our sight, leaving behind no proton, no electron, no trace, just absence? The cracks widen further when cosmology joins the stage. The neutron lifetime is not just an arcane number for laboratory notebooks. It is written into the fabric of the cosmos itself. In the first 3 minutes after the Big Bang, when the primordial fire cooled enough for protons and neutrons to combine, the neutron lifetime determined the balance of hydrogen and helium that emerged. Shift the neutron's life by even a few seconds, and the elemental recipe of the universe changes. Cosmologists compare the predicted abundances of these light elements with what we observe in the stars, in galaxies, in the cosmic microwave background. The match is imperfect. Some suggest the discrepancy in neutron lifetimes is connected to the very birth of the cosmos, that the neutron carries within it a secret woven into the Big Bang itself. And then comes the darker speculation. If neutrons can decay into unseen particles, what else might they conceal? Could they open doorways to forces outside the Standard Model? A fifth force beyond the 4 we know? Could they be portals to parallel sectors of reality where invisible particles mirror our own, carrying away energy like smugglers in the night? Even in their decay, neutrons resist clarity. They disassemble into a proton, an electron, and an antineutrino. But the antineutrino, elusive and ghostly, is notoriously difficult to measure. Could it be that we have misunderstood its role, that the balance of energy in neutron decay hides deeper currents? The cracks spread into theory as well. The Standard Model explains neutron decay as a consequence of the weak nuclear force, mediated by heavy W bosons. Yet the persistence of the lifetime discrepancy hints that the weak force may not be the whole story. What if there are hidden mediators, lighter particles slipping through unseen? What if the decay paths are more numerous, more complex than we dare imagine? The widening cracks invite both awe and dread. If the neutron harbors new physics, then every atom in your hand is linked to realms beyond our knowledge. Every stone, every breath, every star is tethered to a mystery that defies resolution. Imagine holding a rock, feeling its solidity, its weight. You assume it is stable, its atoms locked together in bonds unyielding. Yet within, the neutrons whisper a different story. Their lifetimes fluctuate, their deaths uncertain, their allegiance split between the world you know and the worlds you cannot see. The rock's stability rests on a foundation that quivers, a bridge suspended over hidden abysses. The bad guys close in further as experimental ingenuity pushes the frontier. Some teams design more refined bottles, using magnetic fields to eliminate wall collisions that might skew the count. Others perfect the beam method, increasing precision in proton detection. Yet instead of agreement, the rift persists. Like two clocks ticking out of sync, each insisting on its truth. The more closely we look, the more the neutron slips through our grasp. In this uncertainty lies danger. If the standard model is incomplete, then decades of assumptions may need to be rewritten. The neutron, long considered solved, may yet prove to be a cipher pointing toward a hidden order of physics. The cracks widen, not merely in our measurements, but in our very understanding of reality. And so we stand in a moment of unease, the triumph of theory undone by the stubbornness of experiment. The neutron, instead of a solved riddle, becomes a mocking enigma, its behavior hinting at hidden universes, invisible decays, unknown forces. It is here that the story darkens, the certainty dissolves, and the weight of mystery bears down. If even the neutron cannot be trusted, then what of the world it builds? What of the stability of atoms, of stars, of ourselves? The cracks have widened too far to ignore. What once seemed a closed chapter now stands open, the ink running, the meaning uncertain. And somewhere in the silent heart of the neutron, a secret waits, one that could undo the story of matter itself. The bad guys are no longer at the gates. They are inside the citadel. The neutron was meant to be the silent guardian of stability, the invisible glue that kept the atomic world intact. For decades, its existence seemed assured, its role understood. Yet now, as the cracks widen, we find ourselves staring into a chasm of uncertainty so deep that even the foundations of physics tremble. This is the collapse of certainty. The feeling is not unfamiliar. In human history, there are moments when the pillars of belief crumble. When the Earth, once thought fixed at the center of creation, was revealed to orbit the Sun. When Newton's clockwork universe gave way to Einstein's pliable space-time. When determinism dissolved in the haze of quantum uncertainty. Each collapse brought not only revelation, but dread. The sense that the world you thought you inhabited was, in fact, a shadow of something stranger, darker, and more elusive. So it is with neutrons. Their measured lifetimes disagree, their decay paths hint at the unseen, and their very nature resists definition. The standard model, that proud cathedral of modern physics, insists it has the answers. Quarks and gluons bound within the neutron, the weak force guiding its decay, the mathematics precise to many decimal places. Yet the experiments whisper dissent. They tug at the threads of certainty, and as those threads unravel, so too does the illusion of closure. Imagine holding a neutron in your mind's eye. You picture it as a small, neutral bead of matter nestled beside protons in the nucleus. Yet this picture is already a fiction. Inside, it is not a bead, but a storm, a swirling sea of quarks bound by gluons, their energy more real than their substance. The neutron is not a thing, but a process, a storm momentarily balanced. And even that storm is not still. It decays inevitably into something else. But what if, in some instances, it decays into what we cannot see? What if the process leads not to matter we know, but to matter that hides from every instrument we wield? Here lies the collapse. If neutrons harbor channels into the invisible, then our grasp of reality is incomplete. Every atom rests on a foundation we cannot wholly describe. The rock in your hand, the blood in your veins, the stars overhead, all of them rely on the neutron's stability, and yet the neutron itself is unstable, dissolving with secrets intact. For the physicist, this collapse of certainty is a nightmare and a thrill. To admit that the neutron may be a doorway to dark matter is to concede ignorance, but also to glimpse possibility. To suggest that it decays through channels unknown is to risk rewriting textbooks, but also to approach the edge of a new era. Yet for the rest of us, for the human mind seeking solidity, it is an existential dread. If the very particles that hold the world together cannot be trusted, then what truly is real? This is the all-is-lost moment in the story of science when the ground beneath us gives way. Decades of carefully constructed theory cannot reconcile the experimental cracks. Precision, once thought definitive, now reveals only ambiguity. The neutron, once an emblem of certainty, becomes a symbol of doubt. In the laboratory, the collapse is palpable. Physicists, once confident in the consistency of their models, now argue in conferences and papers. Some defend the standard model fiercely, insisting the discrepancy is a mirage, an artifact of measurement. Others push boldly toward new physics, suggesting the cracks are not mistakes but revelations. The debates echo with both hope and despair. For every voice that sees promise in the neutron's mystery, another laments the failure of clarity. But the collapse of certainty does not belong to the physicists alone. It belongs to all of us. For the neutron is not confined to laboratories. It is in your bones, in your breath, in the starlight that falls upon your skin. It is the reason matter exists at all. And if that foundation is unstable, then the very notion of permanence, of solidity, falters. Think of the sun. Its fire is sustained by nuclear fusion, a process balanced delicately by the forces within. Neutrons play their silent role in that cosmic dance. Without them, the stars would falter, the universe would dim. Yet here we are, questioning whether those neutrons are fully known. The collapse of certainty is not abstract. It is cosmic, it is existential, and perhaps it is also humbling. For too long, humanity has imagined itself in command of knowledge, as though the universe were a puzzle already nearly solved. Yet the neutron reminds us that the puzzle is deeper than we dared imagine. Every answer reveals new questions, every measurement new mysteries. Certainty collapses, not because the universe is broken, but because our vision is partial, our reach limited. The haunting possibility is this: what if the neutron is not merely misunderstood, but unknowable? What if its full truth lies forever beyond us, its secrets locked in interactions too subtle, too fleeting, too hidden to grasp? Could it be that certainty itself is an illusion, that physics, like philosophy, like art, will never arrive at completion, but only at deeper and deeper shadows? This is the weight of the collapse. Not only that the neutron defies us, but that it mocks our need for closure. It whispers of a universe built on instability, where even the glue of matter is not what it seems. And in that whisper lies a warning: do not mistake stability for certainty, nor permanence for truth. Yet collapse is not the end. It is the turning point. Every era of science has faced it. The collapse of geocentrism, the collapse of determinism, the collapse of solidity itself when atoms were revealed as mostly void. Each collapse felt like loss, but each cleared the ground for revolution. So too with neutrons. Their uncertainties may be the very cracks through which new light will pour. But in this moment, all feels lost. The laboratories echo with doubt, the theories strain under contradiction, and the very idea of matter's foundation trembles. Certainty, once taken for granted, lies in ruins. And as you contemplate the neutron, decaying silently, perhaps into matter unseen, you feel the same tremor. What if the neutron, the most unassuming of particles, is the undoing of certainty itself? The collapse has come. What rises from it remains unknown. Picture a universe stripped of neutrons. At first glance it seems a minor subtraction, one type of particle among many, a detail in the cosmic story. But remove them, and the edifice of existence collapses. This is not a gentle unraveling, but a catastrophic implosion of possibility. Start with the atom. Without neutrons, protons stand alone in their cages of electric repulsion. Each proton carries a positive charge, and like charges repel. Without neutrons to separate them, to dilute their hostility, the nucleus is a powder keg. Hydrogen might remain, a solitary proton wandering the void, but all heavier elements would disintegrate before they could form. No helium, no carbon, no oxygen, no iron. No chemistry as we know it. A universe without neutrons is a universe where matter itself refuses to grow. Now picture the stars. Their lives depend on fusion, on protons pressing close enough for the strong force to overcome their electric repulsion. Neutrons are the silent mediators in this cosmic forge. They stabilize nuclei as the fire climbs the periodic table, as stars build new elements in their cores. Without neutrons, fusion stops at hydrogen. The stars themselves falter. They may ignite briefly, their fuel burning erratically, but they collapse almost as quickly as they form. No long-lived suns, no golden light to warm planets, no stellar furnaces to seed the cosmos with life's ingredients. Extend the thought to the grandest scales. Galaxies form from clouds of gas cooling, condensing, and fragmenting into stars. But if stars cannot live, galaxies cannot shine. They become faint, sterile gatherings of hydrogen mist, lit only by the rare sparks of unstable fire. The universe is a desert, vast, empty, and silent. The dark night of the soul is not only physical, but existential. Imagine being born into such a universe. You would never draw breath, for oxygen would not exist. You would never carve words into stone, for stone itself requires silicon and iron. You would never lift your eyes to the stars, for stars would never burn. Without neutrons, there is no story, no memory, no meaning. The universe is not merely lifeless, but lightless, an endless expanse of hydrogen solitude. This vision is not fantasy. It is what the equations tell us. The neutron is not an optional detail, but a keystone in the arch of existence. Remove it, and the arch falls. Keep it, and the arch rises into galaxies, stars, planets, and us. This duality reveals the fragility of the cosmos. Life hangs on the narrow balance of a particle that itself is unstable. Neutrons decay in minutes when left alone, and yet in the crowded embrace of the nucleus, they persist for billions of years. Stability is not guaranteed. It is borrowed, conditional, precarious. And so the dark night deepens. If neutrons are uncertain, then so too is everything they support. What if tomorrow the balance shifted? What if neutrons began to decay more quickly, destabilizing the atoms in your body, the oxygen in your lungs, the carbon in your blood? The thought is terrifying, but it underscores a truth. Existence is not solid, but contingent. The neutron's very presence is a miracle of balance, a knife edge on which the universe dances. This realization weighs heavily on the human spirit. We crave permanence, yet the neutron tells us permanence is an illusion. We crave solidity, yet the neutron reveals solidity is an arrangement of storms, fleeting and unstable. In the dark night of the soul, we confront this fragility. We see that the universe is not inevitable but improbable, not certain but precarious. And yet, the very fact that we can imagine this universe without neutrons reveals something profound. We live in the narrow slice of possibility where neutrons exist, where they balance protons, where they hold matter together. Out of countless potential universes, ours permits complexity, chemistry, and consciousness. This is not chance in the trivial sense. It is chance elevated to destiny, to necessity. If neutrons were absent, there would be no one to mourn their absence. Their existence and our own are inseparable. Consider the stars again, not as they might have been, but as they are. In their cores, neutrons make possible the alchemy of fusion. In their deaths, they are born again in torrents of collapse, as protons and electrons merge into vast seas of neutrons. These neutron stars remind us of what could have been, had the balance tilted differently. They are monuments to compression, remnants of stellar collapse, whispers of universes denied. And yet, from their extremes, we learn what is possible in ours. This vision of absence sharpens our gratitude for presence. The neutron is not simply real, it is vital. Without it, the universe is sterile. With it, the universe is alive. In this tension lies the paradox. The neutron itself is unstable, yet its instability allows stability on scales unimaginable. Its impermanence gives rise to permanence. Its fragility gives rise to strength. The dark night of the soul is a confrontation with loss, but it is also a prelude to transformation. To imagine a universe without neutrons is to glimpse the abyss that could have been. To return from that abyss is to understand more deeply why our universe matters. It is not inevitable. It is not secure. It is precious beyond measure. The neutron is not simply a particle, it is the gatekeeper of possibility. Without it, the story ends before it begins. With it, the story unfolds into galaxies, stars, planets, and life. To confront its absence is to recognize the miracle of its presence. But this recognition brings new questions. If neutrons are so fragile, so precarious, what does that say about us? What does it say about the meaning of existence? Are we too fleeting arrangements of balance, temporary storms that hold for a moment and then pass? The neutron teaches us that stability is not the norm, but the exception, not the foundation, but the miracle. And that realization haunts us. The dark night of the soul does not resolve the riddle. It deepens it. We see the void that would have been, and we shudder. But from that shudder comes the whisper of possibility. Perhaps the neutron is not a final answer, but an invitation. An invitation to seek, to question, to marvel at the improbable balance that sustains us. Without neutrons, the universe would be silent. With them, it sings. And yet, the song is fragile, the harmony delicate, the chorus fleeting. In the silence of the dark night, we hear both the absence and the presence, both the despair and the awe. And we are left with a question that cuts to the marrow. If even the neutron is so precarious, then what does that make us? The neutron is not what we once believed. For decades, we treated it as a particle in the simplest sense, a small, solid constituent of matter, a building block like a Lego brick in the grand edifice of the universe. It sat comfortably alongside the proton and the electron in our textbooks, one of the holy trinity of atomic architecture. But as the anomalies grew, as experiments revealed their defiance of certainty, a radical truth began to dawn. The neutron may not be a thing at all, it may be a process. This realization is not without precedent. In the 20th century, physics has repeatedly shattered our illusions of solidity. Atoms, once thought indivisible, proved to be clouds of probability. Protons and neutrons, once imagined as simple spheres, were revealed as swarming seas of quarks and gluons. Even the vacuum itself, far from being empty, is alive with fluctuations, particles springing in and out of existence like ghosts. The neutron is the latest step in this march, a reminder that the deeper we look, the less thing-like reality appears. Think of the neutron not as a bead, but as a storm. Within it, 3 quarks, 2 downs and 1 up, whirl in a sea of gluons. These gluons, carriers of the strong force, do not sit passively between the quarks but interact with one another, creating a dense, dynamic field of energy. The majority of the neutron's mass does not come from the quarks themselves, which are almost weightless, but from the violent interplay of gluons, the constant creation and annihilation of virtual particles. The neutron is less a particle than a miniature cosmos, its apparent stability arising from a balance of chaos. Now recall the neutron lifetime puzzle, the discrepancy between bottle and beam experiments. This too suggests the neutron is not a single stable entity, but a shifting process, its decay path branching unpredictably. When trapped, neutrons behave one way. When streamed, they behave another. Perhaps neither measurement is wrong. Perhaps both are glimpses of a deeper truth. The neutron is not a fixed particle with a single destiny, but a probabilistic process that can take multiple routes, some visible to us, others hidden. Here lies the breakthrough. Stop thinking of the neutron as a thing and start thinking of it as an event. The neutron exists not as a permanent object, but as a continual unfolding, a momentary arrangement of forces, a fragile balance of instability. Its decay is not an aberration, but its nature. Its persistence within nuclei is not permanence, but participation in a larger process of balance. The neutron is not an island. It is a crossing point of forces, a temporary resonance in the cosmic symphony. This reframing transforms the way we think about matter itself. If neutrons are processes, then atoms are not solid edifices, but patterns of stability in a sea of flux. The world is not built from blocks, but woven from dances, from storms that persist long enough to give the illusion of solidity. You too are not a collection of things, but a choreography of processes, chemical reactions, electrical signals, quantum balances, sustained for a time before dissolving. The neutron becomes a metaphor as well as a particle. It teaches us that stability is not achieved through rigidity, but through tension, through the balancing of opposites. Protons repel one another, but neutrons mediate their hostility. Alone, the neutron is unstable. Together, in the nucleus, it becomes the guarantor of stability. This paradox mirrors our own condition. We are not stable in isolation, but in relation. Not permanent as individuals, but enduring through connections, through processes larger than ourselves. The idea of the neutron as a process also opens new frontiers in physics. If decay can proceed through multiple channels, some visible, some hidden, then perhaps neutrons are our window into the dark sector, into forces and particles that do not interact with light. The missing seconds in the neutron lifetime puzzle may be the footprint of new physics. The neutron may be showing us through its instability that reality is broader than the standard model allows. It may be less a particle of matter than a messenger of possibility. Consider again the neutron star. It is not a simple mass of particles, but an ocean of processes pushed to extremes. In its depths, neutrons may dissolve into quark matter, into superfluids that flow without resistance, into exotic states that defy our models. The star is a reminder that neutrons, when gathered in immense numbers, reveal their processual nature most clearly. They are not beads stacked together, but storms merging into storms, a collective process on a cosmic scale. This breakthrough also reshapes how we see time. If the neutron is a process, then its decay is not an end but a transformation. It becomes a proton, an electron, an antineutrino. It is never lost, only changed. And if the neutron itself is a pattern of forces, then its decay is simply a reconfiguration of that pattern into others. Permanence is an illusion, persistence is reality. What does this mean for us? It means that the world we inhabit is not made of things but of flows, of processes. Your body is not built from permanent bricks, but from storms like neutrons, balanced for a time. Your thoughts, your memories, your very consciousness are not objects but processes unfolding in time. To exist, is to persist, to balance instability for long enough to be noticed. The neutron, humble and hidden, thus becomes a teacher. It tells us that the search for solidity is misguided. We should not seek permanence but embrace process. We should not imagine reality as static but as dynamic, not a wall but a wave. The collapse of certainty was not the end, it was the doorway. Through it, we discover that reality is richer, stranger, and more alive than we dreamed. And yet, this breakthrough is not closure. It opens further questions. If neutrons are processes, what does that say of protons, of electrons, of space and time themselves? Are they too storms, patterns, resonances in a deeper sea? What lies beneath these processes? What canvas sustains the dance? The breakthrough does not solve the riddle. It deepens it, transforming despair into wonder. So we return to the neutron, no longer a bead, no longer a certainty, but a storm, a process, a fragile, fleeting pattern that holds the world together for a time. It is less than we thought and more than we imagined. It is not real as a thing, but real as a balance, as an event, as a momentary persistence in the endless flow of the cosmos. The breakthrough is humbling. It tells us that to seek reality in objects is to miss the point. Reality lies in patterns, in processes, in the storms that sustain themselves on the edge of collapse. And in this realization, the neutron becomes not just a particle of physics, but a parable of existence. The neutron is not real as a thing, it is real as a process. And that truth reshapes everything. The neutron is no longer simply a silent particle hidden in the atomic nucleus. It has become something else, a lens, a mirror, a key. Through it we confront the fragility of matter, the instability that underlies stability, and the deep paradoxes that shape reality itself. To redefine the neutron is to redefine what it means for anything to exist at all. For centuries, humanity sought the indivisible. From Democritus to Dalton, from Rutherford to Chadwick, we imagined that reality must rest on unchanging pieces, particles solid and permanent, enduring beneath the flux of the world. The neutron, when discovered, seemed to fulfill that dream. Neutral, elusive, yet essential, it slotted neatly into the atomic story. It balanced protons, stabilized nuclei, and completed the symmetry of the atom. It was the missing piece. But that dream has dissolved. The neutron is no more indivisible than the atom, no more permanent than the stars it helps to build. It is a storm of quarks and gluons, a fragile balance of forces, a process of decay. Its neutrality is a mask, its stability conditional, its existence a question mark. To cling to it as a thing is to cling to illusion. To see it as a process is to awaken to a deeper truth. Reality itself is not made of objects, but of relationships, not of bricks, but of dances. This realization redefines the very idea of real. If neutrons are not things but processes, then so too are protons, electrons, and perhaps even space-time itself. What we call matter is not a collection of parts, but a choreography of interactions. Existence is not solidity, but persistence, not permanence, but balance. The neutron's lesson is universal. What is stable is not the absence of change, but the harmony of change. Consider again the nucleus. Protons repel one another violently, their electric charges screaming for separation. Yet neutrons intercede, not by force but by neutrality. They stand between, diluting the repulsion, balancing the storm. This is not the stability of stone but of tension, of forces opposed yet reconciled. The neutron is a mediator, a silent negotiator in the heart of matter. Without it, atoms collapse. With it, the world holds. This balance echoes across scales. In neutron stars, the collapse of matter produces not destruction, but transformation. Protons and electrons, pressed beyond endurance, merge into seas of neutrons. Here, in the densest objects known, we glimpse matter pushed to its limit. Yet even there, neutrons may dissolve, giving way to quark matter, superfluids, or stranger states we cannot yet imagine. Even in their most extreme collective form, neutrons teach us that stability is always provisional, always contingent on deeper processes. Redefining reality through neutrons also reshapes how we think about time. The neutron decays in isolation, its average lifetime a mere 15 minutes. Yet in nuclei it persists for billions of years. Its fate is not absolute, but contextual, not fixed, but relational. Time itself is revealed as conditional. The persistence of matter is not a property of particles alone, but of the patterns they form together. Reality is not composed of eternal entities, but of temporary alliances. This insight reverberates into philosophy. We long for certainty, for permanence, for bedrock. But the neutron shows us that bedrock itself is shifting sand. The foundations of matter are processes, not pillars. The universe is a symphony, not a statue. To redefine reality through neutrons is to accept impermanence not as loss, but as essence, instability not as flaw, but as truth. It also reshapes our self-understanding. You are composed of neutrons, billions upon billions of them, stabilizing the atoms of your body. Yet they are not things you have. They are storms sustained in balance, processes unfolding in time. Your solidity is borrowed, your persistence conditional. You, too, are not a thing but a process, not a permanence but a balance. The neutron is your mirror. And this redefinition ripples outward into the cosmos. For if neutrons are processes, then the universe itself is process. Stars form, burn, collapse. Galaxies swirl, collide, disperse. Even the vacuum seethes with fluctuations, a quantum storm of ephemeral particles. The universe is not built from pieces but from patterns, not from permanence but from persistence. The neutron is the microcosm of this truth, a storm that holds just long enough to allow everything else to exist. But this redefinition is not mere abstraction. It has consequences. The neutron lifetime puzzle, the stubborn discrepancy between bottle and beam experiments, may yet reveal new physics. Perhaps neutrons decay into dark particles, into matter we cannot see but that shapes galaxies. Perhaps their instability points toward new forces, new symmetries, new realities. The neutron may be the portal through which we glimpse the next revolution in physics. What we call a crack may in fact be a doorway. To redefine reality through neutrons is also to embrace humility. The standard model, triumphant as it is, may be incomplete. Our theories, precise as they are, may be parochial. The neutron reminds us that certainty is always provisional, that science itself is a process, not a product. The collapse of certainty was not defeat but invitation. The breakthrough was not closure but opening. The neutron is not the end of inquiry, but its renewal. This finale, then, is not a conclusion but a transformation. We entered with the question, are neutrons even real? We imagined them as things, as blocks, as objects. We emerge with a deeper truth. They are storms, processes, balances. Their reality is not solidity but persistence. Their lesson is not permanence but pattern. And what of us standing here, fragile beings of flesh and thought? The neutron tells us that our reality too is provisional. We are not fixed but flowing, not eternal but persistent for a time. Yet in that persistence lies beauty. For just as the neutron holds the world together, so do we hold our lives, our meanings, our connections, balancing instability into harmony. The neutron redefines reality, not by destroying it, but by deepening it. It shows us that the universe is stranger, more dynamic, and more alive than we dared to dream, and in that strangeness lies awe. But the neutron leaves us with a question, one that lingers like a shadow. If even the foundation of matter is only a process, only a storm sustained on the edge of collapse, then what is the true nature of reality itself? Hold out your hand, look at it carefully. You see solidity, flesh, weight. You trust it, for it has carried you through every gesture of your life. Yet beneath the skin and bone, beneath the cells and molecules, beneath the very atoms themselves, lies a truth stranger than you can imagine. Your hand exists only because storms of balance hold for a moment before dissolving. Every rock, every tree, every star is the same. They are not things but balances, not certainties but negotiations. At the heart of each atom, protons press desperately against one another, their charges demanding separation. The only reason they do not fly apart is because neutrons intervene, standing silently between them, neutral and invisible, mediating the conflict. The world holds together not because of strength, but because of balance. The neutron is the quiet storm at the center of it all. Its neutrality is not emptiness, but potential. Within it, quarks whirl in chaos, bound by gluons that tie and retie their knots with relentless energy. It is not a bead, not a block, but a seething process. And yet, out of this storm comes the stability of matter, the solidity of your hand, the endurance of the world. But the neutron itself is fragile. Left alone, it decays. In mere minutes, it collapses into a proton, an electron, and a ghostly antineutrino. Its life is temporary, its stability borrowed. And yet, when gathered with others, when held in relation, it persists for billions of years. This paradox defines it: unstable alone, stable together. The neutron is a storm that only survives by balancing with others. This image mirrors us. We too are not stable alone. Our lives gain meaning only in connection, our persistence only through relationship. Like neutrons, we are fragile storms that endure when woven into larger patterns. The lesson of the neutron is not simply about matter, it is about existence itself. Imagine again the rock. It feels solid in your hand, timeless, immutable. Yet it is not. It is storms of neutrons, mediating the rage of protons, balancing forces so great they could tear it apart in an instant. The solidity you feel is an illusion, the persistence of storms that, without neutrons, would dissolve into chaos. The rock is not a thing, it is a balance. Extend this to the stars. Their fire burns because neutrons allow protons to fuse, to build heavier elements. Their light endures because neutrons stabilize nuclei against collapse. Without neutrons, there would be no stars, no light, no warmth. The cosmos itself is a storm of balance, sustained only by these neutral mediators. And extend it further still, to yourself. You are alive because neutrons exist. Your body is built of carbon, oxygen, nitrogen, iron, all forged in stars that relied on neutrons to endure. Every breath you take, every heartbeat, every thought is possible because of storms that persist at the subatomic scale. You are not separate from the neutron. You are its expression. You are storms of balance made flesh. This final image, then, is haunting and beautiful. We began with the illusion of solidity, of permanence. We asked whether neutrons, the silent glue of matter, are even real. We discovered they are not things but processes, not objects but storms. And now, at the end, we see what that means. Reality itself is storms of balance, fleeting yet persistent, fragile yet enduring. The neutron teaches us that the universe is not a statue carved from stone but a symphony played in time. Every note fades, yet the harmony persists. Stability is not the absence of decay, but the weaving of decay into persistence. Existence is not permanence but balance, storms holding just long enough to become stars, rocks, hands, lives. And so we return to the question, are neutrons even real? The answer is both no and yes. No, they are not real as solid things, as immutable blocks. But yes, they are real as processes, as balances, as storms. Their reality is not in permanence but in persistence, not in being but in becoming. Look once more at your hand. It is storms balanced on the edge of decay. Look at the world around you. It too is storms. Look at the stars above. They are storms as well. The universe is not built of things but of balances, not of permanence but of patterns. The neutron reveals this truth, and once seen, it cannot be unseen. And so the haunting question lingers. If even the neutron is only a storm, then what does that make us? We are storms too, storms of balance, fragile and fleeting, yet capable of wonder. The same processes that hold the neutron together hold us together. The same balance that sustains matter sustains meaning. The neutron does not diminish us, it illuminates us. It shows us that to exist is to balance, to persist in the face of decay, to hold long enough to become something more. This is the storm of balance, the final image of the neutron. Not a particle, not a block, not a certainty, but a storm that makes the universe possible. And in that storm, we find ourselves. Thank you for joining us on this extraordinary journey through the universe, here on Frontiers of Infinity. If this glimpse into the unknown has sparked your curiosity, be sure to subscribe and join us where we unravel the darkest mysteries of space.